Hello friends, welcome to the video lecture series on digital image processing. I am Dr. Dafda, and in this 26th video class of DIP, we will study the next topic of image restoration and reconstruction, that is restoration in the presence of noise only spatial filtering. In our 23rd video class of DIP, we saw that the image restoration can be done by the inverse filtering or the deconvolution. But that is the case when the degradation is present due to blurring or artifacts and not only noise, right? So at that time we have to use the frequency domain filtering. But if only noise is present in the image, then spatial filtering is the method of choice of removal of noise. So you know what is restoration? Restoration means to bring back to the position as if it was not degraded by any noise or artifacts or blurring. And noise also you know that is the unwanted variations in the intensity levels of our image. Spatial filtering means the filtering in the image plane domain itself, and for the spatial filtering we will not be going to the frequency domain, or we will not be taking the Fourier transform of the image and doing the filtering. We will be doing the filtering by applying the filter mask on the image itself, right? So let us start. So starting with the slide which we saw in the 23rd video class of DIP, the model of image degradation and restoration process. So from this slide you can see that the image can be degraded by some degradation function h as well as some additive noise n of x, y. When only the degradation present in the image is a noise and h of uv is not present, this equation will become g of uv is equal to f of uv plus of n of uv. Then you may think that you can remove the noise by subtracting it from g of uv to obtain f of uv and hence f of xy, but this is not the realistic option. Why? Because this noise is a random noise and we do not know the exact nature of this noise, and of course we can do that, but if the noise is known like the periodic noise that we discussed in the previous video class or 25th video class of DIP, so there we were knowing that the noise is periodic noise and hence we were subtracting the noise by choosing the filter h of uv that gets the noise subtracted from this, and hence you obtain f of uv. But when only the additive noise is present, spatial filtering is the method of choice. So this is the slide that we saw in video lecture number 15, spatial filtering techniques in DIP and its implementation in MATLAB. So here we saw that the spatial filtering can be of two types, the smoothing spatial filters and sharpening spatial filters for the removal of noise. And this smoothing spatial filters can be linear filters or mean filters or averaging filters, and non-linear or order statistics filters. So these averaging filters, which we have already learned in video lecture number 15, are not only the averaging filters that exist. Some others also exist, such as geometric mean, contraharmonic mean and harmonic mean filters. Arithmetic mean filter is nothing but the averaging filter, and weighted averaging filter is one in which the weight of the mask is not same, it is different for different elements. Similarly, the non-linear or order statistics spatial filters, which we learned in our video lecture number 16, order statistics or non-linear filters in DIP and its implementation in MATLAB, are not only the minimum filter, the maximum filter and the median filter, but there is also one other type of filter such as alpha trimmed mean filter that we will be learning here. And as we have already implemented the linear filters and non-linear filters, or the mean filters and the order statistics filters in MATLAB in video lecture number 15 and 16, here we will not be implementing those in MATLAB because the filters that we will be learning here can also be similarly implemented in MATLAB. Let us go ahead. So you know what these filters do? The spatial filters replaces the value of the center pixel on which we are keeping the window or kernel by the value obtained by averaging using such equation, right? So very first filter is the arithmetic mean filter or moving average filter or the averaging filter, which we have already learned in our video lecture number 15, right? So what is done here? We keep the mask on the image and we take the sum of products and divide by m cross n. So let us say, for example, this is our 3x3 image. On this 3x3 image we place a filter mask having values 1, right? We will be multiplying 1 into 1, 1 into 7, 1 into 5, 1 into 6, 1 into 2, 1 into 3, 1 into 1, 1 into 4, 1 into 2 and adding all the values, okay, and divide by m cross n, that is 3 cross 3. So this is how you will obtain the arithmetic mean value of this center pixel. You will get 3.44, rounding off 3.44, you will get the final value as 3. So this 2 will be replaced by 3. And this is how arithmetic mean filter or averaging filter works. So this mean filter is the simplest filter. It is also known as the low pass filter. So this mean filter is useful in removing Gaussian noise as well as uniform noise, which are random noise, and here the noise is reduced due to blurring or averaging, or you can say smoothing, because averaging filters are nothing but smoothing filters. The next mean filter is the geometric mean filter, which is also used for eliminating the Gaussian noise, but of course it is not effective for the pepper noise, and it also achieves smoothing like the arithmetic mean filter, but here the advantage is that it loses less image details as compared to the arithmetic mean filter. The geometric mean filter is given by this equation, where this pi represents multiplication, right? So this pi represents multiplication, whereas here this represents the summation. So taking the same image, rather than adding these values, you have to multiply all the values raised to 1 upon mn, that is 1 upon 9, which will give you 2.78, and rounding off 2.78 you will get 3. And see the example of geometric mean filter. This is our original image that is corrupted by additive white Gaussian noise, and when you apply arithmetic mean filter to this noisy image, you will obtain the output image like this. But if to the same noisy image, if you apply the geometric mean filter, you will obtain a better output like this, in which you can compare these two outputs and see that here image details that are lost are very less as compared to this arithmetic mean filter. The next mean filter is the harmonic mean filter, which is given by this equation. So harmonic mean filter is also used for removing noise like Gaussian noise, and it also works well for the salt noise, but it fails to remove pepper noise or black dots in the image. So for our same image, if we find out the harmonic mean filter, it is mn, that is 3 cross 3, that is 9, upon 1 upon all the values, right? And here you will get 2.19, which can be rounded off to 2. So the next filter is the contraharmonic mean filter. As the name suggests, it is contradictory, or you can say opposite to the harmonic mean filter. Harmonic mean filter was working well for salt noise only and was not working good for pepper noise, whereas contraharmonic mean filter is suitable both for salt noise as well as pepper noise. So you can say it is a complementary of the harmonic mean filter and is given by this equation. Here Q is the filter order. The positive value of Q is suitable for eliminating pepper noise, and the negative value of Q is suitable for eliminating salt noise, and hence you can say that this filter is useful for removing impulse noise or salt and pepper noise. So in this equation, if you keep Q is equal to 0, the filter will become arithmetic mean filter. Say if you keep Q is equal to 0, this term will become g of st raised to 1, okay, and if you keep Q equals to 0 over here, that means this term raised to 0, that means it is 1, okay, so it will only remain this term, okay, and this term is nothing but the arithmetic mean filter. Similarly, if you place Q is equal to -1, then the filter will reduce to a harmonic mean filter. Why? Because keeping Q is equal to -1 over here, this will become 1 upon g of st, which is this, right? And this term will not be present. Let us go ahead and see the example for these filters. So for example, the image is corrupted with pepper noise with noise PDF of 0.1, and this is the output image that is obtained using contraharmonic mean filter with Q is equal to 1.5. So here you can say that the pepper noise is removed. And if you corrupt the same image with the salt noise and filter that with a contraharmonic mean filter of Q is equal to -1.5, you will obtain such a image. So depending on the value of Q, it will remove either the salt noise or pepper noise, but it cannot do both simultaneously, as you can see from this equation, right? Next are the order statistics filters, which also we have learned in video lecture number 16, and of course also implemented in MATLAB. So here we'll be starting with one of the slides of video lecture number 16, and you can see here how this order statistics filter works. So for order statistics filter, we'll be keeping this filter mask, which is you can say an empty mask, over the image, and we will be ordering the pixels in the ascending order like this. And after the ordering, we'll be choosing some particular value, for example the median value, the minimum value, or the maximum value from these ordered values, and we'll keep that particular ordered value in the place of the value of pixel in the image like this. The order statistics filters are not based on convolution, right? Here what we are doing, we are arranging in specific order and then choosing the values, right? So the types of these order statistics filters are the median filter, where it will choose the median values after ordering. Okay, so we will take the example of the same image. So we'll arrange these values in the ascending order like this. We will choose the median value. So there are total 9 values and the median value will be the fifth value, right? And the fifth value is 3. So we'll replace this 2 with this 3 in the output image. Next one is the max filter, in which we'll be choosing the maximum value out of the ordered values, and you know that the maximum value of these values is 7. So we'll be placing the 7 value over here, and obviously this will be used for reducing the dark noise or pepper noise. Why? Because the dark noise will be towards 0. Okay, and if you are choosing the maximum value, that means the dark value is removed or pepper noise is removed. Conversely, for the minimum filter, we'll be choosing the minimum value, that is 1 over here, and obviously this will be used for reducing the bright noise, or you can say the salt noise. Why? Because salt noise will be towards 255 in the image, right? So it will be removed. This median filter is used for removing both salt and pepper noise. Maximum filter is used for removing the pepper noise. Minimum filter is used for removing the bright noise. And one other filter is also there, which is known as midpoint filter. So here the equation is like this: f cap of xy is equal to 1 by 2 of max of g of st plus minimum of g of st. So 1 by 2 of maximum value is 7. So we will take 7 over here, plus minimum value is 1. We will take 1 over here. So you will get 8 by 2, which is equal to 4. For midpoint filter, we will be replacing this value with the value 4 in the output image. So this midpoint, you can see from this equation, is nothing but the average of the minimum and the maximum values, and it is very effective in removing Gaussian noise and uniform noise. So this figure shows image corrupted by salt and pepper noise. This is the result of applying filter of 3 cross 3, and if you again apply the median filter to this filtered image, you will get a better result like this, and again applying the median filter to this, you will get still better result, as you can see here. This shows the minimum and maximum filters. This is the image corrupted with pepper noise. So when you apply the maximum filter, you obtain the output image like this, which removes the noise. And when the same image is corrupted with salt noise and you apply the minimum filter, you will obtain the output image like this. Now the filters which we have seen up till now are helpful for removing either Gaussian noise or salt and pepper noise, but they cannot do both of them, right? So what is the solution to that? The solution to that is the alpha trimmed mean filter. So as the name suggests, it is trimming or cutting alpha values, right? And then finding out the mean value of the remaining pixels. What is alpha? Alpha is equal to d by 2. And what is d by 2? D by 2 is the lowest gray level values and the highest gray level values. So total values which will be removed will be equal to alpha, and therefore it is known as alpha trimmed mean filter. Getting it? Right? So as the name suggests, it is also a mean filter. That is, it is similar to the averaging filter, but the difference here is that we can clip some of the values from the lower values and the higher values and then find the mean value, and hence this one will be helpful in removing Gaussian noise as well as salt and pepper noise. So you can say that it is based on the concept of computation of the average of the pixels that fall within some particular window, this window starting from here to here. So this is the equation for the alpha trimmed mean filter. F cap of xy is equal to 1 upon mn minus d summation of gr of s t. In this equation, if you keep d is equal to 0, it will become arithmetic mean filter. So arithmetic mean filter will not be having this d value, right? But if you keep d is equal to mn minus 1, it will become a median filter. And if you choose the values in between d is equal to 0 to mn minus 1, then it will be able to remove both the salt and pepper noise as well as Gaussian noise. So alpha trimmed mean filter removes the d by 2 highest and d by 2 lowest intensity values. The average of the remaining mn minus d values is called the alpha trimmed mean filter. Let us understand this with the same example of our image. So our image is a m cross n image which is equal to 9. Now let us choose the first case of d is equal to mn minus 1 Okay, so let d is equal to mn minus 1, then the d will be equal to mn is 9, so 9 minus 1 which is equal to 8. So this is d. What is alpha? Alpha is equal to d by 2, so d by 2 will be equal to 8 by 2 which is equal to 4. Okay, so what does it mean? It means that trim alpha, so trim alpha is equal to 4 on both the sides of the ordered values of the pixels, right? So what we will be doing here, we will be trimming these 4 values, the lowest 4 values, and trimming these 4 values, the highest 4 values. So remaining is 3. Okay, only the median value will remain. So that is for the case mn minus 1. So when d is equal to mn minus 1, it becomes a median filter. But we do not want to only remove the salt and pepper noise or only the Gaussian noise. We want the intermediate combination. Okay, so let us choose d is equal to mn minus 2. So it will become 9 minus 2 which is equal to 7, and alpha will be equal to 7 by 2 which is equal to 3.5, which is not the valid choice. Why? Because you cannot remove 3.5 values on both the sides. It should be an integer number, right? Next, let us take the third case. So d is equal to mn minus 3, that is 9 minus 3 which is equal to 6, and so alpha will be 6 by 2 which is equal to 3. So trim 3 on both the sides of these ordered values. Okay, so we will be trimming, you can see this color. Okay, we will be trimming these 3 values, these 3 values, and what is remaining? That is 2, 3 and 4, right? So remaining values we will sum up and find out the mean value. Okay, so 2 plus 3 plus 4 divided by 3 which is equal to 9 by 3 which is equal to 3. Okay, so 3 will be your answer when you take d is equal to mn minus 3. If you take d is equal to mn minus 4, you will find 9 minus 4 which is equal to 5, and alpha will be equal to 5 by 2 which is equal to 2.5. Again, it is not an integer value, so it is not the valid option. Let us choose d is equal to mn minus 5. It will become 9 minus 5 which is equal to 4. Therefore, alpha will be equal to 4 by 2 which is equal to 2. So you have to trim 2 values. So see this green color, we are trimming these 2 values and the last 2 values. Okay, so what will be remaining? 2 plus 2 plus 3 plus 4 plus 5. So 5 values divided by 5 will give you 16 by 5 which is equal to 3.2, which can be rounded off to 3. Okay, so again you will get 3 as your mid pixel value which needs to be replaced over here, right? Next, let us choose d is equal to mn minus 6. So 9 minus 6, 3, alpha by 2 is equal to 1.5, which is again not a valid option. Let us choose d is equal to mn minus 7. Okay, so 9 minus 7 which is equal to 2. Therefore, alpha by 2 is equal to 1. So we will trim only one values. Okay, so see this color, we will trim only this one because remaining values will be 7, right? So 23 divided by 7 will give you 3.28, which will again be rounded up to 3. Let us choose d is equal to mn minus 8. Okay, so 9 minus 8 which is equal to 1, and alpha by 2 will be equal to 0.5, which is again not a valid option. And let now choose d is equal to mn minus 9. Okay, so now what will happen? We will be selecting all the pixel values, right? So 9 minus 9 which is equal to 0. Okay, so d has become 0 now. Okay, see, when d is equal to 0, it becomes arithmetic mean filter. Let us see here. So d is equal to 0. So alpha is equal to d by 2, that is 0 by 2 which is equal to 0. So trim 0 values. So all the values you have to choose. When you sum up all the values, it will come out to be 31 divided by 9 will give you 3.44, which can be rounded up to 3. You can see here that when you are choosing d is equal to 0, okay, it has become a arithmetic mean filter. So these all calculations I have just shown to make you understand that what happens when you choose different values of mn minus d. So you can start with mn minus 2, which is not a valid option. Okay, so choose mn minus 3. So your correct answer for this particular image of alpha trimmed mean filter will be 3. So 3 is the correct answer. I hope it is clear. Let us go ahead and see the image example of alpha trimmed mean filter. So you can see here the original figure which is corrupted with additive uniform noise, and this figure is still more corrupted with addition of salt and pepper noise also along with this uniform noise. Now if you use a arithmetic mean filter of 5 cross 5 mask size, you will obtain such a result. And if you use the geometric mean filter, this will be the result that will be obtained. And obviously you can see that geometric mean filter is not performing much well in this case of both the noises present. Going ahead, for the same corrupted images, if you apply the median filter, it will be providing good result, but it is not able to remove the uniform noise completely, and the image that is obtained using alpha trim mean filter is much successful in removing both the salt and pepper noise as well as the uniform Gaussian noise. So finally, you can compare all the 4 results of 4 different filters. So this one is by using arithmetic mean filter, which is not giving good results. Using geometric mean filter, the results are still worse. Using median filter, the results are good but not much clear, as still the Gaussian noise is visible in the image. But when you apply the alpha trim mean filter, you can see that the image has become much clear with the removal of both salt and pepper noise as well as the uniform Gaussian noise. For example, if you compare these 2 results, you can see that this one is giving much smoother output as compared to here. Okay, here it is removing the details in the image, whereas the same details are preserved over here. Why? Because it is also using the averaging. Okay, whereas this one, median filter, will not be using the averaging process. Right? Even here you can note the image details are retained also here and here. So in conclusion, the alpha trim mean filter is much successful in removing both the salt and pepper noise as well as the Gaussian noise. So that is all for this video class. I hope you would have gained a good knowledge from this video lecture. Thank you very much.